Welcome to the module on well test analysis. The objective of this course is to help you understand the basics of well testing analysis, and will cover crucial topics such as types of well tests, process of well testing, well test interpretation, its significance, review and procedures, and importance of well tests at different stages of field development. Let us begin by a brief introduction and understanding the activities to well test. The aspect of petroleum engineering that distinguishes it from other engineering disciplines is that petroleum engineers do not design the systems they work with. Unlike an engine designed by a mechanical engineer or a structure designed by a civil engineer, the oil and gas reservoirs are given to the petroleum engineer. In petroleum engineering, the system is not physically accessible, and engineers have to rely on indirect measurements to determine the properties of the system. Transient testing is the general case that encompasses measurement of flow rates and pressures under various conditions. Activities to well test. Well tests assume that a well is producing oil at a constant rate of XSTB/D for a period of Y hours. The well is then shut in. The bottom hole pressure of the well will decrease, or draw down, as production begins and will increase, or build up, when the well is shut in. How the pressure change is a function of the properties of the reservoir system. Disturbing the reservoir by changing the flow rate of a well and observing the resulting pressure change is a noisy experiment that may be run to determine the dynamic reservoir properties indirectly. Changing the rate and measuring the pressure in the same wellbore is a single well test. The change in pressure in the offset well is smaller than in the active well, and there is a time lag between the beginning of the change in flow rate and the corresponding change in pressure at the offset well. Changing the flow rate in a well and measuring the pressure response in another well is a multiple well test. Transient testing also involves measuring the change in flow rate due to pressure changes or the change in flow rates of individual layers as a result of a change in the total flow rate of the well. Well testing. A reservoir is in a transient state when the pressures or saturations of fluids are changing with time and the rate of change is different at different locations. Monitoring flow rate and pressure while the reservoir is in a transient state yields valuable information about the properties of the reservoir system. Well testing is an inverse problem, that is, the system input, production rate history, and system output, pressure response, are known and the properties of the system, reservoir, are to be determined. Alternative to conventional well testing include wireline formation testing, continuous monitoring with permanent gauges, rate transient analysis, log-derived permeability estimates and core analysis. Well test interpretations. Significance. Two major tasks of the well test interpretation are model identification and parameter estimation. Parameter estimates are meaningless if an appropriate model is not selected for interpretation. Well test parameters estimation methods may be grouped into one of three classes: 1. Straight line methods, 2. Type curve methods, and 3. Simulation/history matching. The logarithmic scales comprise late time data such as 90% of the data fall in last log cycle of the graph. Example, for infinite acting radial flow, the last log cycle also represents 90% of the reservoir volume investigated during the test. Relying on a single graph scale for interpretation may cause important behavior to be overlooked, leading to invalid results, and should be avoided. Well test interpretations. Well test interpretation is the process of obtaining information about a reservoir through examining and analyzing the pressure transient response caused by a change in production rate. It is important to note that the information obtained from well test interpretation may be qualitative as well as quantitative. Identification of the presence and nature of a no-flow boundary or a down-dip aquifer is just as important as, if not more important than, estimating the distance to the boundary. Comprehensive interpretation of acquired data is critical for efficient reservoir development and management because it quantifies the parameters that characterize the dynamics response of the reservoir. Review. Data processing. Transient well tests are conducted as a series of dynamics events triggered by specified changes in the surface flow rate. During interpretation, it may be desirable to analyze just one particular event or all events simultaneously. In either case, the data must first be processed. The first step in data processing is to split the entire data set into individual flow periods. A high density of data is needed only for early time transients. Therefore, special algorithms are usually employed to reduce data set of a manageable size because of the nature of the pressure disturbance propagation. Algorithmic sampling is preferred. The sequence of events should incorporate the recent flow rate changes observed during the test. This enables rigorous accounting for superposition effects. The shape of pressure transient curve is affected by the production history of the reservoir. Each change in production rate generates a new pressure transient that passes into the reservoir and merges with the previous pressure effects. pressure trends observed at the wellbore results from the superposition of all the pressure changes. The next step is to transform the reduced data so that they display the same identifiable features regardless of test type. After the data are transformed, the task of identifying the flow regimes begins. Procedure: collect the data necessary for the interpretation. Review quality control and prepare the data for interpretation. Deconvolve the test data. Identify the flow regimes present in the test data. Select the reservoir model to use for interpretation. Estimate the parameters that characterize the model using manual straight line and log-log methods. Simulator history match the pressure response. If appropriate, calculate confidence intervals. Interpret the estimated model parameters. Validate the results. Types of well tests. Deliverability tests. The primary objectives of deliverability tests are to obtain fluid samples, to determine well deliverability, to determine the well potential, or to develop inflow performance curves for system analysis. Transient tests. Primary objectives of transient tests may include to estimate in situ permeability to oil or gas, to estimate average drainage area pressure, to evaluate stimulation treatment effectiveness, and to estimate drainage area and/or fluids in place. Multi-well tests. In a multi-well test, the rate is changed at one well, the active well, and the pressure response is measured at one or more offset, or observation, wells. Multi-well tests are often more complex than single-well tests. Multi-well tests are usually run to quantify the degree of communication between wells or to estimate directional permeability. Single-well tests. In a single-well test, the rate is changed, and the pressure response is measured at the well being tested. Objectives of single-well tests may include to quantify the degree of damage or stimulation, to estimate the in-situ permeability, to estimate the drainage area or fluids in place, and to estimate the average drainage area pressure. Drawdown tests. In a drawdown test, the reservoir is initially at uniform pressure, and the well to be tested is shut in. The well is open for production, ideally at constant flow rate, and the resulting pressure response is measured as the pressure draws down. Build-up tests. Here, the well has been producing for a period of time, thus creating a pressure gradient in the reservoir. The well is shut in, and the resulting pressure response is measured as the pressure builds up. Exploration well tests. For a well test on an exploration well, the focus is on the entire reservoir. Objectives of an exploration well test usually include fluid sampling, estimating initial reservoir pressure, evaluating well productivity, estimating distances to boundaries, and estimating fluids in place. Exploration well tests often must be conducted while the rig is on location, making such tests extremely expensive. The expense is justified by the major investment decisions that will be made based on the information obtained from the test. Development well tests. In contrast, in development well testing, the focus is on the individual well and the near wellbore area. Objectives of a well test on a development well might include estimating average drainage area pressure, evaluating stimulation treatment effectiveness, quantifying wellbore damage, and estimating reservoir permeability. Compared to exploration well tests, development well tests are relatively inexpensive. The results of development well tests are used in minor investment decisions such as whether or not to do a stimulation treatment. Pressure buildup testing. These tests are conducted by first stabilizing a producing well at some fixed rate, placing a BHP measuring device in the well, and shutting in the well. Following shut-in, the BHP builds up as a function of time, and the rate of pressure buildup is used to estimate well and formation properties, such as average drainage area of the well, and skin factor in the region immediately adjacent to the wellbore. Pressure drawdown testing. A pressure drawdown test is conducted by producing a well, starting ideally with uniform pressure in the reservoir. Rate and pressure are recorded as functions of time. The objectives of a drawdown test usually include estimates of permeability, skin factor, and, on occasion, reservoir volume. These tests are particularly applicable to new wells, wells that have been shut in sufficiently long to pressure stabilize, wells in which loss of revenue incurred in buildup test would be difficult to accept. Multiple rate testing. Two-rate flow test. The two-rate test can be used when estimates of permeability, skin factor, or reservoir pressure are needed and economic considerations preclude the well from being shut in. Pressure buildup tests. Note that, for the two-rate test to be valid, the second rate must be kept strictly constant or the test interpretation may be substation LI in error. N-rate flow test. The method presented for analyzing the two-rate test can be extended to N-rates also. Gas well testing. Flow after flow test. In this testing method, a well flows at a selected constant rate until pressure stabilizes to pseudo-steady state is reached. The stabilized rate and pressure are recorded. Rate is then changed and the well flows until the pressure stabilizes again at the new rate. Isochronal test. The objective of isochronal testing is to obtain data to establish a stabilized deliverability curve for a gas well without flowing the well for sufficiently long to achieve stabilized conditions. Modified isochronal test. The objective of modified isochronal tests is to obtain the same data as in an isochronal test without using the sometimes lengthy shut-in periods required for pressure to stabilize completely before each flow test is run. In modified isochronal test, shut-in periods of the same duration as the flow periods are used, and the final shut-in BHP, PWS, before the beginning of a new flow period is used as an approximation to average P in the test analysis procedure. Injection well testing. Injection test. The injection wells may be as numerous as the producing wells. Consequently, testing injection wells is particularly important for efficient planning and operation of both secondary and tertiary recovery projects. Satisfactory injection performance over a long period of time and prompt detection of increasing wellbore damage are important to the economics of any recovery project. This method is for determining average reservoir pressure and for analyzing composite systems in non-unit mobility reservoirs. Fall-off test. Fall-off test in an injection well is analogous to pressure build-up testing in a production well. An idealized fall-off test is conducted by injecting at a constant rate before shut-in at time Tp. Pressure data taken immediately before and during the shut-in period are analyzed with the methods developed for pressure build-up tests. Multiple well testing. Interference testing. A solution for the unsteady state pressure changes with time at any point in the reservoir caused by a change in flow rate at another point. Pulse testing. An interference test in which the flow rate at the active well is changed several times in the form of a series of alternate flow and shut-in periods instead of producing the well at a single constant rate. Importance of well tests. Importance of well tests at different stages of field development. Initial case, DSD tests to confirm dry or producing wells. Exploration tests, to collect the sample and estimate the pressure. Injectivity tests and fall-off tests, injection wells and particularly for to understand the mobility ratio. Interference tests and pulse tests, effect of the production of one well over the other while creating a disturbance. Well test interpretation plays a role in many stages in the life of the well including exploration, appraisal, development, reservoir characterization, and production engineering. Exploration and appraisal. Reservoir engineering. Reservoir simulation. Production engineering. Reservoir characterization. Exploration and appraisal. The information gained through well testing will be instrumental in making major investment decisions such as whether to set a platform, build a pipeline, develop a field, or sign a long-term production contract. The two most important questions that well testing and exploration and appraisal wells can address are: how much oil or gas does this reservoir contain? And at what rate can wells in this reservoir produce? Flow tests are often used during exploration testing. These tests are designed to investigate enough of the reservoir to assess the economic viability of the prospect. The deliverability is obtained from the flow rates achieved during the test. Reservoir engineering. What is the in situ permeability? What is the nature of and distances to reservoir boundaries? What is the average reservoir pressure? Reservoir simulation. A knowledge of the in situ permeability is important in reservoir simulation and production forecasting. The nature of and distance to reservoir boundaries is important in reservoir simulation and in well spacing decisions. The average reservoir pressure is used in reservoir simulation, well optimization, and material balance calculations. Production engineering. The focus in production engineering is on the individual well. The well testing and production engineering reflect this focus. Is the well damaged? How effective was the stimulation treatment? Reservoir characterization. Poor well performance may be caused by reservoir characteristics, such as low permeability or low reservoir pressure, by near wellbore conditions, such as damage from mud filtrate invasion, non-Darcy flow or plugged perforations, by some combination of these factors. Well test interpretation can help identify the cause of poor well performance, so that the appropriate remedial action may be taken. Thank you for learning with us.